In today's video we will examine a basic circuit to safely bring 5 volts onto a PCB using a USB Type-C connector. Specifically, we will use the Molex 105-450-0101, which is a USB 3.2 Gen 2 surface mount receptacle. Molex provides high-quality documentation, a schematic symbol, and a PCB footprint for this connector. I've chosen the TCPP01M12 protection IC from ST Microelectronics. This IC protects against V-bus overvoltage, CC to V-bus short-circuiting, ESD protection on the CC pins, and over-temperature. The TCPP01M12 datasheet contains an example circuit in Figure 21 on page 18. Let's now create this for ourselves in KiCad. Here is the rough draft of the circuit. Looking at J1 first, you can see that I've connected pins A1, B1, A12, and B12 to ground. Pins A4, B4, A9, and B9 provide power and are labeled V-bus-C for V-bus connector. Pins A5 and B5 provide the configuration channel and are labeled CC1C and CC2C, respectively. The remaining pins are not connected because for this circuit we only need power. Moving on to IC1, we can check that all the pins are connected consistently with the example circuit provided by ST. The most important signal is V-bus control, which is defined by the R1 and R2 resistor bridge. Now we must ask, how are the resistances of 10 k ohms and 2.7 k ohms selected? To answer this question, we can look at page 5 of ST document UM2773. Table 1 shows the relationship between the R2 resistance and the connector's V-bus overvoltage threshold. For example, if R2 is 2.7 k ohms, V-bus is limited to 6 volts, and if R2 is 620 ohms, V-bus is limited to 22 volts. Thus, in our schematic, if V-bus-C exceeds 6 volts, IC1 will turn off Q1, and the system power output V-bus, connected to the N MOSFET source, will fall to 0, protecting the downstream components. It appears we've implemented the functionality we wanted, so, can we move on to PCB layout? No, we cannot, for several reasons. First, we have not specified the exact components for Q1, D1, R1, R2, and C1, and, consequently, these symbols do not have an associated PCB footprint. Second, the ERC found errors and issued warnings. While some warnings can be ignored, ignoring errors is risky because the main purpose of the ERC is to identify electrical errors that might prevent the board from functioning correctly. On this channel we will not move on to PCB layout if the ERC has identified any errors. And, lastly, the schematic itself is a bit ugly, making it harder than it has to be to understand the functionality. Let's make some changes. First, we must perform component selection. Obviously there are many factors to consider, but this discussion is out of scope for this video. Here we can simply review my selections. For Q1, I've selected the ST-STT6N3 LLH6 N-channel MOSFET. I also downloaded the symbol and footprint from SAMXSys and imported them into KiCad. After adding the symbol to the schematic, we can replace Q1. For the resistors and capacitor I've selected 0603 package components with high stock availability from JLC-PCB. Specifically, R1 is a Yaejo RC0603FR0710KL, R2 is a Yaejo RC0603FR072K7L, and C1 is a Yaejo CC0603KRX7R9BB104. This update is made by filling in the manufacturer name and manufacturer part number fields in the symbol field and then selecting an appropriate generic footprint, for example, a Hansalda 0603. Lastly, for D1, I've selected an ST-BAT54K film and used the SAMXIS provided symbol and footprint. Running the ERC again shows the errors and warnings still exist. How can we fix the ERC error? Input power pin not driven by any output power pins? If you ask the internet, or a chatbot, how to fix this error, it will tell you to connect a power flag to the net. Luckily, doing this does actually correct the error. Now, to address the ERC warnings, we must modify the J1 symbol. This brings us to the third reason we could not move on to PCB layout. Our schematic is a bit ugly and difficult to understand. The symbols have a large effect on the ugliness and understandability of the schematic because they force the connections to be made in a particular way. Additionally, as we see here, a symbol can also create ERC warnings when the pin types are not correctly defined. Let's add a customized version of J1 into the schematic and connect it. The remaining two warnings can be fixed by including the library in the footprint field value. So, why is this customized J1 better? All unused pins are unconnected by default. The pin names reflect the signal name. VBus and ground pins have type power input. CC1 and CC2 pins have type bidirectional. The VBus pins are grouped at the top. The ground pins are grouped at the bottom. The S1 pin, connected to the connector's shield, is included. Lastly, the footprint from Molex, using UltraLibrarian, which did not connect the shield to ground, is replaced with a built-in footprint that does. Let's now insert custom symbols for IC1 and Q1 and rewire the schematic. Now our schematic matches the example schematic from ST and is easier to understand. Running the ERC shows one error and two warnings. We will address these in a future video. However, in the next video we will introduce the net class feature and add notes to improve understandability.